For this example, I will ask you to recall with me the definition of a symmetric matrix. A matrix A is symmetric if its transpose is equal to itself. Now, as such, this can only apply to square matrices, otherwise the two matrices would be different sizes. So what we're going to do is determine if the set of 2 by 2 symmetric matrices is a subspace of the set of 2 by 2 matrices. So with that in mind, we need to check for a total of 3 axioms here. Those axioms are going to be A4, A1, and A6. A4 is the existence of the zero vector within the subspace. A1 is closure under vector addition, and A6 is closure under scalar multiplication. So to start with A4, we're going to check to see if the zero matrix, what's a good notation for that? The 2 by 2 zero matrix. We'll check to see if that's symmetric. Now, given that the first row is 0, 0, and the second row is 0, 0, and the first column is 0, 0, and the second column is 0, 0, I would say this is definitely equal to its own transpose. As such, the zero matrix is contained within the subset of 2 by 2 symmetric matrices. For A1, closure under vector addition, we'll let A and B be symmetric 2 by 2 matrices. As such, we can say that A transpose is going to be equal to A and B transpose is going to be equal to B. What we want to do is show that A plus B is going to be equal to its own transpose. So what we'll do is we'll start with A plus B transpose. We're going to show that this thing is equal to A plus B. So the first thing that we're going to do is apply a property of transposes that says that transpose will distribute over matrix addition. And then we'll apply the above property. A transpose will be equal to A, and B transpose will be equal to B. Therefore, A plus B transpose is going to be equal to A plus B. Therefore, the set is closed under vector addition. And finally, for A6, we'll say let C be a scalar. We want to show that the transpose of C times A is going to be the same as, we want to show that C times A is also a symmetric 2 by 2 matrix. So what we'll do is we'll take a scalar multiple of matrix A, and to show that it's symmetric, we will take the transpose of that. Now there is a property of transposes that says that if you take the transpose of a scalar multiple of a matrix, that's the same as taking the transpose of the matrix first and then multiplying by the scalar. However, because A transpose is equal to A, this will be equal to C times A. Therefore, we just showed that the transpose of C times A is the same as C times A. Therefore, C times A is also a symmetric matrix. So because all 3 of these axioms hold, therefore, the set of symmetric 2 by 2 matrices is a subspace of the set of all 2 by 2 matrices. Now in this proof, an important thing that I never used except in the actual definition of the zero matrix was the size of the given matrix. As such, this proof will extend nicely to 3 by 3 matrices, 4 by 4 matrices, 5 by 5 matrices, and more generally, n by n matrices.